Mercury, the planet closest to the Sun, might seem initially unremarkable and uninteresting, but it holds many mysteries. Despite its scorching surface temperatures, there's water at its poles, and the surface of Mercury astounds astronomers with its unique impact craters and geological features that remain unexplained by modern science. Surprisingly, despite its small size, Mercury boasts a magnetosphere that shields it from solar winds and even possesses a minor atmosphere, which defies expectations. Today, we'll delve into the enigmatic world of Mercury and uncover the secrets of its surface. Mercury measures approximately 1,516 miles in radius and orbits the Sun at an average distance of only 36 million miles, about 2.5 times closer than Earth. Consequently, a year on Mercury lasts only 88 Earth days. The planet's temperature can soar to a blistering 800 degrees Fahrenheit, but plummets to a bone-chilling minus 290 degrees Fahrenheit at night due to its extremely thin atmosphere. Moreover, Mercury has an incredibly slow rotation. A single day on Earth is equivalent to 59 days on Mercury. This results in day and night on the planet lasting for 3 Earth months. The cause of this sluggish rotation isn't due to tidal locking with the Sun, as previously thought. Instead, Mercury is in a 3-to-2 spin orbit resonance with the Sun, rotating on its axis 3 times for every 2 orbits around the Sun. Scientists believe that this resonance may have been in place since Mercury's formation, while others suggest it might have shifted due to a significant collision with another celestial body. Mercury's eccentric orbit is another factor that influences its rotation and temperature. This orbit, shaped like an elongated egg, causes Mercury's distance from the Sun to fluctuate between 29 million and 43 million miles. Surprisingly, recent discoveries have revealed that Mercury also has a thin, 9 million mile wide dust ring orbiting it, created by meteoroids and space debris sharing the same orbit as the planet. This phenomenon could be more common in exoplanet systems than previously thought. Despite its diminutive size, Mercury boasts a magnetic field, although it's the smallest in the solar system, with only 1% of the strength of Earth's. This magnetic field, though weak, deflects stellar winds and forms a magnetosphere. However, this magnetosphere may have leaks, allowing sunlight to penetrate, as observed by the Messenger Space Telescope. Mercury's substantial core, which accounts for 1/3 of the planet's total mass, is a critical component in generating its magnetic field. It's a sizable core, roughly 1,289 miles in radius, which is half the size of Earth's. This unique composition is attributed to the early stages of our solar system, when a high concentration of heavy metals near the young Sun contributed to Mercury's core development. However, Mercury could have been even more massive in the past, but various hypothetical cataclysmic events may have stunted its growth. Potential scenarios for Mercury's evolution include gravitational interactions with Earth and Venus, impacting other large celestial bodies, or suffering massive collisions that stripped away a significant portion of its mantle. These hypotheses remain speculative, and further studies, including missions like the Bepi-Colombo mission by the European Space Agency and the Japan Aerospace Exploration Agency, are expected to shed more light on the origin of Mercury and the inner planets of our solar system. Mariner 10 and Messenger, though we're keen to learn more about Mercury, face significant challenges when it comes to studying this planet up close. Ground-based telescopes find it exceedingly difficult to observe Mercury due to its proximity to the Sun, which makes nighttime tracking complicated. The Sun's intense light can also damage optics when observing Mercury for extended periods during the day. Furthermore, reaching this small planet is more challenging than even the most distant planets in our solar system, primarily due to the Sun's powerful gravitational pull and extreme temperatures. As a result, spacecraft sent to explore Mercury must approach it with great caution, making the journey lengthy and risky. These spacecraft must operate within stringent temperature limits. This is why only 2 missions, Mariner 10 and Messenger, have been dispatched to Mercury. Without them, our knowledge of Mercury would be significantly limited. Mariner 10 made history as the first mission to utilize the gravitational pull of another planet, Venus, for its maneuvers. It harnessed solar radiation pressure on its solar panels and carried a wealth of instruments. Mariner 10 confirmed Mercury's crater-covered surface, detected its magnetosphere and thin atmosphere, and made a groundbreaking discovery of the planet's substantial core. It also measured temperatures on both sides and captured over 2,700 images of Mercury, contributing to the creation of a map covering nearly half of the planet's surface. While it didn't orbit Mercury, Mariner 10 made 3 passes over the planet, with each pass 6 months apart. Its mission lasted about a year, and it ceased transmitting signals in late March 1975, likely continuing to orbit the Sun. 30 years later, the Messenger spacecraft continued the work in 2004. Unlike Mariner 10, Messenger not only flew by Mercury, but also became the first spacecraft to orbit the planet, providing more comprehensive and intriguing data. Messenger aimed to collect information on Mercury's chemical composition, its exosphere, study the magnetic field and its sources, and investigate the planet's geological history and core's present state. Before entering Mercury's orbit, Messenger completed 3 orbits around the planet to slow down. By 2014, it had captured around 200,000 photos of Mercury and 2,500 images. However, Messenger began running out of fuel in early 2015, ultimately crashing into Mercury, creating a new crater. Overall, the Messenger mission spanned about a decade, leading to numerous unexpected discoveries. One of the most remarkable findings was the creation of a comprehensive map of Mercury, showcasing all the craters and basins on its surface, enabling scientists to study its geology and depth. Additionally, Messenger determined the planet's chemical composition, revealing that its surface comprises 46% oxygen, 12% magnesium, 26% silicon, 7% aluminum, and 4% calcium. The spacecraft also indicated a significant presence of sulfur, with less iron, suggesting past volcanic activity and a potential magmatic ocean covering the planet at one point. As the planet cooled, heavy elements like iron settled deeper, explaining their lower presence on the surface. This magma phase filled the atmosphere with volatile substances. The magma activity also melted the planet's interior, but didn't significantly reduce Mercury's mass. As it cooled, the planet began to shrink, resulting in surface cracks and ridges. Messenger also discovered water deposits at Mercury's poles, where water exists in the form of ice, unaffected by the sun's direct rays due to the pole's unique conditions. This finding hints at the possibility of liquid water beneath the surface. Messenger also unveiled an unexpected revelation concerning the planet's magnetic field, revealing a 20% shift along its axis, which could have effects on solar particle intensity and weathering elements on the surface. Finally, Messenger managed to capture a photo in 2011 from the orbit of a planet that depicted the entire solar system, except for the dim Uranus and Neptune. The last time such an image was taken was way back in 1990 by the Voyager 1 spacecraft. Interestingly, the most captivating discovery from both of these missions was the surface of Mercury. Let's delve deeper into this remarkable planet. Mercury's surface boasts a fascinating topography. Despite being predominantly covered in craters, it also features relatively smooth areas, along with ridges and troughs. Pinpointing the exact number of craters is a challenge, but we've identified around 567 so far. These craters are named after prominent individuals and are primarily the result of impacts from small cosmic bodies. They can be categorized as simple or complex, based on factors like geological variations, peak formations, and multiple rings on the surface. Simple craters, prevalent in the southern region, typically range from 0.6 to 9 miles in size and are less than 7 miles deep. In contrast, complex craters, though less common, are larger, stretching from 10 to 168 miles in length and deeper than 7 miles. Mercury hosts more of these topographic features than any other object in the solar system, with 110 craters sporting central peaks, as opposed to just 17 on the Moon. Apart from the average-sized impact craters, there are even larger ones known as impact basins, which can extend up to 200 miles or even a whopping 963 miles. The higher number of craters on Mercury can be attributed to the planet's limited atmosphere and the increased speed of objects in its solar orbit. Two of the most renowned basins on Mercury are Caloris and Rembrandt. Caloris, the largest, measures a staggering 963 miles in diameter and was once filled with lava, resulting in smooth plains at its base. It's believed that the impact that formed Caloris might have also created Mercury, characterized by furrows and plains. Rembrandt, the second largest crater, is roughly half the size of Caloris and likely experienced a similar lava-filling process, giving its surroundings a smooth appearance. In addition to these basins, Mercury showcases various intriguing craters. The Beethoven Basin stands out as the planet's oldest crater, possibly dating back over 4 billion years. It is also home to the darkest spot on Mercury, covered in volcanic ejecta. Furthermore, Mercury features some special and rare crater types, including elliptical, polygonal, and ghost craters. Elliptical craters form due to the low velocity and large volume of the impacting object, constituting around 2 to 4% of the planet's surface. Polygonal craters, with their distinct angles, are believed to arise from the planet's crust structure and degradation, numbering around 33 on Mercury. Ghost craters, though barely visible, exhibit ridges along their edges, formed from the rapid accumulation of lava flows. Another fascinating crater type, commonly found on the Moon as well, is the ray crater. These craters are characterized by long rays extending from the impact site, with their length varying. The longest rays on Mercury, like those of Hokusai spanning 2,800 miles, are indicative of younger craters. The brightness of these rays diminishes over time, allowing scientists to estimate the relative ages of these craters. Young craters often have terraced walls, while older ones tend to be shallower, possibly filled with volcanic material. Studying the variety of crater types and sizes on Mercury provides valuable insights into the planet's geological history and helps estimate its age. Caleb Fassett, a NASA researcher, made an intriguing observation about Mercury: a significant absence of craters ranging from 12 to 80 miles in diameter. He proposed that this unusual phenomenon might be due to the frequent creation of inner crater planes during the planet's early history. Mercury boasts relatively few high surface features like ridges and escarpments, with only about 100 identified across its terrain. These highland formations were shaped at different times and through various geological processes. For instance, smooth ledges resulted from volcanic activity, while ridges and wrinkles emerged during the planet's cooling and compression phase. On average, these features reach heights of 0.07 to 0.5 miles, with exceptions like Antoniadi Dorsum, an extraordinary mountain range on Mercury that can stretch up to 360 kilometers in length, a feature not found on Earth. Despite extensive research on Mercury's surface, the global history of its compression remains a puzzle. Approximately 27% of the planet's surface consists of nearly perfectly smooth plains, adorned with few craters. These vast plains are scattered across all latitudes and surround large basins. About 2/3 of them were shaped by volcanic activity, while the remaining third likely resulted from volcanic material ejected during the Caloris Basin impact event. One more unique characteristic of Mercury is its hollows, a geological oddity not observed on any other celestial body. These shallow, edgeless depressions with flat bottoms cover approximately 0.08% of the planet's surface, often within impact craters. Scientists speculate that hollows are relatively young features formed by the loss of volatile materials from the surface. This ongoing process implies that Mercury's surface could continue to evolve over time, potentially leading to significant changes. In fact, experts believe that 99% of Mercury's surface may undergo transformation within the next 25 million years. Mercury holds great significance for studying the dynamics of surface changes and understanding how various landforms form. Consequently, in 2018, a new spacecraft was dispatched to observe this intriguing planet. Named Bepi Colombo, this mission consists of 2 separate spacecraft that will observe Mercury from both near and far. The primary mission is to address the questions raised by its predecessor, Messenger. Bepi Colombo will delve deeper into the origin and causes of Mercury's magnetic field displacement, the presence of water deposits at its poles, the nature of cavities on the planet, and the mechanisms behind their formation. By 2025, Bepi Colombo is expected to enter Mercury's orbit and embark on its main scientific exploration. This new study has the potential to unlock many of the planet's mysteries, offering insights that can significantly enhance our understanding of the history of our solar system.